All right. Good afternoon, everybody. So this is week 6. This is the last. The last week before the break. We're gonna have a 2 weeks break, okay? Because there is reading week and there is actually the National Day. So there will not be any lecture for like 2 weeks. That said, there is no midterm in this course, but you are working on project 2. So let me talk about project 2 here. So hopefully project 2, it's not going to be as hard as project 1. Okay, project 1 was hard, I understand, because you had to kind of get familiar with the code base. You had to get familiar also with a new type of programming, which is kind of event based, right? The fact that you have events, which is interrupt, kicking in at any time, and kind of like causing a lot of synchronization problems and so on. This is maybe very new for you, right? So you had to get used to a lot of things. Hopefully you have learned a lot in this process, and then project 2 will be a little bit easier on that side. That said, project 2 still comes with like stuff you have to learn, stuff you have to read, and it might be a little bit difficult also in the beginning to understand what's going on. Okay, so same thing, start early and make sure actually to get to a good kind of a good setup right away. Here, if you go to the project, there is like 4.2 suggested order of implementation. Read that carefully, okay? And here at the end, it says, after you have done this kind of minimal setup here, you should be able to run some user program. Okay, project 2 is about like actually running user programs. If you're done with the setup, which is actually doing the system call setup, you should be able to run some programs. Okay, if you reach that point, and that it's going to be hard to reach that point, but if you reach that point, it means you understand the setup, you understand how system call works, and so on and so forth. Meaning from here, it's just adding code. Right? It's still like, you will have to understand what you add and so on. But once you reach that point, I have good faith that you can complete the assignment. But if you don't reach that point, or if you reach it too late, that's going to be hard. Okay. Sorry, you cannot see the screen. Okay. Let me share the screen. Sorry about that. All right. Sorry about that. Anyway, I was just showing like actually the website. Okay, so I wasn't showing anything important, but here, so section 4.2 in the documentation, in the end it says like after you have done this kind of setup, you should reach a point where you can actually run some programs. Okay, so that's important. Try to reach that point very, very quickly. Okay, I told the TA, the TA are going to talk about that in the tutorial, reach that point before before the end of the week. Okay, if you do that, I'm pretty sure after that it's going to be quite simple. Okay, so don't wait. Start working on homework 2, project 2 right away. All right, let me go quickly to the chat because I can see that. Okay, people say I didn't share. Solution for project 1. No, I will not share a solution for project 1. Okay, because I'm planning to actually reuse those assignments and so on, and I don't want actually the solution to be out. That said, take any book a meeting during office hours or outside with any of us or in the core staff, and we will take you through. Maybe not the solution, but taking you through what's wrong in your design, right? So I think that's more important. All right, so let's move on to the topic of the day. So we are still going to continue talking about memory management, and here, so maybe let me recap quickly what we have seen last week. Last week we talked about virtual memory. What's virtual memory? It's this idea of providing some kind of an abstraction for programmers so that, when I write a program as a programmer, I'm going to see the memory as, I have the entire memory for myself, okay? And I'm going to put my code there, I'm going to put the stack, the heap, and so on, and I'm going to see this virtual memory. So what's happening behind the scenes is that actually this virtual memory doesn't exist, but I have physical memory, and the physical memory stores information about not only my process but every process. Okay, so if I have 100 process in my raw gigabyte system, I will have hundreds of stacks, hundreds of program loaded, and so on and so forth, and heaps and stuff like that. Okay. So why is this virtual memory good? Well, it's good because first of all, it provides some kind of protection. Okay, my program cannot actually access the physical memory of other programs. That's one. The second thing, it actually behind the scene, the memory can place all the code and so on anywhere. Okay, in the physical memory, and it doesn't affect actually my program, because my program actually reasons in terms of virtual addresses. Okay, when I allocate pointers, when I do a jump to functions, and so on and so forth. So that's good as well. And then we have seen this idea of like paging, and paging will basically allow us to translate from the virtual memory to the physical memory, but also like, for example, if we have not enough memory, we're going to be able to actually switch some pieces of the virtual memory, or pieces of the physical memory actually, to the disk, right? It's called swapping. So we have seen that. So here we're going to continue a little bit, and we're going to talk about three big questions here. Okay, the first one is how to allocate free memory. Okay, so how do we track free memory? Where is it? And how do we allocate it? So that's going to be dynamic memory allocation. The other thing is, like when I talked about swapping, okay, swapping means, we're going to move a page or several pages from memory to the disk, okay, because we don't have enough memory and we have usually a huge disk, okay. And the idea is like we're going to swap the page that, we don't need, that the current processes are not needed right now, right? And if they need it later, we're going to swap it back, okay? We're going to page it. But when you have a memory, which page do you evict, right? You need some memory, the memory is full. Which page are you going to put to the disk? How are you going to decide that? Okay, so we're going to look at actually several algorithms, and we call that the page replacement algorithms. Okay, and at the end, maybe a question. Okay, first of all, we'll see if it's really a question, but how much memory to give to each process? Okay, are we going to limit the number of pages they can use, right? And this is going to be called the working set model. And here I'm going to talk about also a little bit how Linux does things and how actually Windows does things, because they manage the memory completely differently. Okay, so let's start with all of these questions. So the first one is like, I'm going to talk about managing free memory. So first of all, when you allocate memory, you have two ways to allocate memory. One is called static allocation. Okay, it's all the variables or data structures and so on that you actually declare in your program, and this data is going to be allocated on the stack. Okay, so this is a typical thing when you allocate, for example, an array, when you allocate a variable, but also when you pass arguments to a variable. All this stuff are going to be done on the stack, right? So these stuff are done at compile time. Okay, so at compile time, we know that actually this is going to be pushed to the stack. Okay, so meaning, you don't write that in C, right? You don't say push to the stack and so on. But when you're going to compile it, this is actually what's going to happen. You're going to generate assembly code that is actually going to push and pop data to the stack, right? This is good. It's simple. It works. It works really well. The only thing is like it's actually restricted, right? So what I mean by it's restricted, well, you probably have done that in A48 or B09, which is, what if you declare, for example, an array and you want this array to grow? Okay, well, you have no choice, right? You have to allocate a new array of a bigger size and you have to copy the data. Okay, you have to do these kind of things, for example. All right, so this is as opposed to dynamic allocation. Okay, what's dynamic allocation? It's basically allocating on the heap. And this is every time you use basically malloc, okay, or calloc or all this stuff. So here the idea is like, you have a data structure, it might increase or decrease dynamically. You don't know that statically, okay? And so all of that is done at runtime. And that's why here we're going to allocate the heap, and the heap is going to be somewhere in the middle, actually in virtual memory, between the stack and the user's code, okay? But managing the heap is actually difficult, okay? And that's what we're going to talk about today, how to allocate free memory on the heap, okay? So what's the idea? The idea here is like you want to allocate or you want to manage actually continuous range of logical addresses, right? Because when you declare an array, for example, usually all of the elements of this array are next to each other. And even if you extend it, they're going to be next to each other in memory, right? It could be complicated if you start to declare an array in one part of the memory, and then the rest of the array is somewhere else, and so on and so forth, right? I mean, you can do that using linked list and so on, right? But if you talk about reallocating contiguous range of data, well, you cannot do that, right? So it's there are two main primitives that you have used. You have used malloc and you have used free, right? And they always tell you you have to free the memory, otherwise this memory on the heap is not going to be allocated, and you might have a memory leak. That's what we call a memory leak, because it's like you allocate some memory, and so it shrinks the free memory that you have, and it can lead to actually filling the memory entirely. Maybe here, let me stop right away. Let's see if you're following. When I talk about allocating the heap, okay, allocating memory, am I talking about allocating virtual memory, or am I talking about allocating physical memory? Okay, everybody talks about virtual. Yes, okay. It is a virtual one, okay. But don't get me, I had this question on Piazza, actually, it's a good question. Don't get me wrong, right? The virtual memory does not exist, right? At the end of the day, when you're going to allocate memory and you're going to store something, it's going to be stored in the physical memory. But now, in the physical memory, is it important that all this data, for example, they are contiguous? Meaning you allocate an array, is it really important that the array is next to each other? Actually, no. Okay, great, you're answering, right? Because of paging. We have seen that, right? In the virtual memory, yes, you're going to allocate page, okay? When you do malloc, if you're going to do that, you're actually going to allocate pages, and they're going to be contiguous. Why? Because it's important, because your program is going to say, go next element, and so on in your array. But so these pages are going to be contiguous in your virtual memory, okay? It looks like they're going to be contiguous, but then in the physical memory, they can be anywhere. It doesn't matter, actually. Okay, so we don't have this problem of contiguous thing. Here in the physical memory, it's going to go wherever we have room, right? So here, yes, we are talking about allocating memory on the virtual memory. Okay, good. So why is heap allocation hard, right? Well, because, if you allocate and then free, and then allocate again, and then free, and then allocate again, and then free, what can happen is like, at some point, your memory will look like some kind of, Frenchies with holes, right? So why is that? Well, we have seen that last week, right? This is called fragmentation. Okay? But wait a second. I said last week, we are actually using paging to avoid fragmentation. So why I'm coming back with this problem of fragmentation? Well, okay, let's take things in perspective here. Paging actually does solve the problem of fragmentation. Okay, why? Because it's a way to actually manage the physical memory by, we put the page anywhere, it doesn't matter. Okay, meaning if we have hundreds of processes together, it doesn't matter where we're going to put it. It's actually going to be pages, and we're going to avoid external fragmentation. That's true. Okay, but now still I'm in the physical memory, and I'm only considering maybe one process. I mean, maybe for sure, I'm going to considering one process, but still, this process allocates memory and wants actually contiguous memory slots, right? Going back to my previous slide here, we want to have continuous range of logical addresses. So here we still have fragmentation, but now it's actually maybe less critical, but still it's at the scale of one process, one program, and allocating memory in its virtual memory. Okay, so still we can have this problem of fragmentation. Okay, so if you do a lot of operation in memory and so on, it might look like this. So why is this a problem? Because the problem of that is like, if you need more memory, if you, for example, you need like a contiguous kind of contiguous range of addresses that is bigger than any of these white holes here, well, you can put it there. Okay, you will have to reshuffle things. Okay, and okay, we still can do that. Okay, we call that compaction, but it's not desirable because if you do that, it's going to waste time. Okay, so you will need to actually do this kind of thing. So we want to avoid fragmentation. We want to avoid holes. Okay. Again, the idea here is like, maybe here I'm gonna talk about the stack, right? For example, why we don't have this problem with the stack? Because the stack actually we do exactly that, right? We allocate the stack, and then as we call functions, we allocate memory for that functions. The function return, we deallocate the memory, we allocate the variables and so on, because we know the size of these variables and so on and so forth. So actually, these kind of things here, this kind of picture, when we say we allocate contiguously everything, yes, we can do it for the stack, but we cannot do it for the heap. Okay, because the heap, we allocate and then we free and then we reallocate and then we free and so on, and we don't know exactly where to put this stuff. Okay, so that's why we have a problem, and that's what we're going to talk about today. Okay, so it's a hard thing, allocate heap. So what's fragmentation? I'm going to talk about it here again. It's the inability to use the memory that is free because it's fragmented. Okay. Why do we have fragmentation? I'm kind of saying that again because first of all, we have different lifetime. Okay, some stuff will be freed before others and so on and so forth. And also we have different size. Okay, maybe at some point you want to allocate an array of like few bytes and then suddenly an array of megabytes, right? So it is completely different depending on what your program is doing. So here we're going to have to make important decisions, and the important decision is like, how do we manage our memory? So first, if we have you do a malloc, you need a block, okay, of a certain size. Where do you put it? Right? You will want to say, okay, I want to put it anywhere I want in memory, okay, but that's not ideal because at some point, what we want is to put it somewhere where it's going to minimize fragmentation. Okay. Also, you might say, okay, I have a large block of memory, but I want to split it into several small blocks and allocate those small blocks. Okay, and you might say, okay, I want to do that with any block. Well, ideally, no. You want to actually do that in such a way that you are going to minimize fragmentation. Okay, and also. You want to actually cursing the free blocks. What do you mean by cursing? Actually, it's called merging. Okay. For example, if you free a block that was before like 20 and suddenly you free a block that was 10, maybe you want to see it from outside as a big block of 30, right? Because if you keep it like 20 and 10, if you need to allocate 30 again, you don't know where to put it, right? Because you don't have such a block. So block, free block that are next to each other, you want to actually merge them. You want to cursive them. In the end, we have to understand the following. Fragmentation, it's impossible to solve. Okay, so there is like theoretical reason that says, for any algorithm you can find, we can create some kind of a sequence of memory allocation that is going to defeat the algorithm, and that's going to create fragmentation to the point where we cannot actually allocate anything. Although we have free memory, but we cannot allocate blocks, okay, of certain size. So avoiding fragmentation is impossible, but we're going to try to do our best, and we're going to try to find the best algorithm that match most of our cases. So we need to design a memory allocator. Okay, so what does this memory allocator needs to do? First of all, it needs to track where is the free space, okay? And at some point, it's going to be it is going to be fragmented somehow. We're going to need to track all of these pieces, okay? What the memory allocator cannot do, right? It cannot control the order and the size of the requested block, okay? This is the program who does that, right? And we don't know how the program is going to be executed, okay? I know the program takes into account variables and so on and so forth, and it can change, you know, its execution. And so we are not going to control the block size, and we're not going to know in advance, right? In the future, we cannot predict actually what's going to be the number, what's going to be the size, and how long the program will need those allocated memory slots. Okay. So it's going to be hard. But what is a good allocator? It's the one that, you know, is going to minimize fragmentation. Okay, that's really important. Okay, why? Because we want to avoid compaction. Compaction is the process of actually reshuffling and reorganizing the memory. But if we talk about, like, you know, moving stuff in memory, it is time consuming, and sometimes it's actually hard, right? Because you need to change pointers, addresses, and so on. If you are in the middle of your program, it could be very, very complicated. Okay, so I say time consuming here, but I should add actually it's hard. Okay, very hard, sometimes impossible. All right, so let's try to find this perfect, or at least the best memory allocator. So first, how do we track memory allocations? The free memory. How do we track which one it's free, right? So one way to do it is actually to have a 1 bit per allocation unit. Okay, again, what are the allocation units we're talking about here? Pages. Okay, if you're using segment, it's going to be something else. But here, if we talk about paging, it's going to be page. So one bit per page. 0 means it's free. 1 means it's allocate. So if you want to kind of map your own memory, the entire memory, you can have it something like this, and then you will need 1 bit per page, right? So if you are looking for a block of n units, if you want to allocate a block of n units, well, it's easy, right? You're going to try to find a series of n zeros into your bitmap. It looks like a good idea. It's actually very compact in terms of what to store in memory, in terms of space, okay? But it's slow. Okay, it's slow, and you have to go through to bits, through the bits and so on. It's not ideal. Okay. Well, okay, I have a question here. Well, if you are unable to find n zeros together, what happens? Well, it means exactly that you have fragmentation. It means that you cannot allocate that. Okay, you cannot allocate that block. Okay, and again, that's the point that we don't want to reach. Okay. By the way, when this happens, usually you have a message in your on your you run a program, and suddenly you have a message saying, "Hey, we're running out of memory," or not enough memory to run the process. That's rare, but it can happen. You might have a segmentation fault. Actually, it depends on the system. Yeah, exactly. Well, yeah, that's when malloc and calloc return mouse. Yeah, correct. So you can also track memory using linked list. Okay, and this is actually the solution that is implemented in the OS. So you have 3 ways to do that. You have free list. You basically have a specific data structure that is a linked list that is going to store addresses. Okay, and that's actually the easiest one, and that's actually the one that is used, right? But there are others that have been proposed. The one is that you don't have a linked list, but you put directly the information inside the memory. Okay. For example, here, here's what's happening here. This, for example, it says 4 blocks are allocated. Okay, and you put it inside the one that is allocated. Here it says 5 blocks are free. 5. Here 4 blocks are allocated, and so on and so forth. Right. So you need a little bit. Maybe you're gonna use 1 page or even less, maybe 1 unit, to actually store information about the entire block. Okay. Another thing here, you can have the same thing, but on top of that, you add pointers to the next kind of free block here. Why is that convenient? Because here, for example, if you want to merge 2 blocks, okay, you need to say the following. So here, for example, let's imagine that. I'm going to take an example here. Let's imagine that the free dot block. Okay. Okay, you can free it, meaning you can put like 4 free. But if you do that, you're going to have 5 free, 4 free, 2 free that are next to each other. You need to merge them, or you need to coerce them. How are you going to coerce them? Well, you need to go through your kind of linked list and find the one before, the one after, and then merge them. But if you have actually double linked list, okay, you can do that very easily, because here you can move to the one before, you can and move to the one after, and you can merge them more easily. So this is more like a convenience to have a double linked list to actually do the operations of merging and so on and so forth. Okay. But roughly this is the same idea. It's like the implicit and explicit. It's the same idea. It's like putting this information directly inside memory. Free list, it's more like, okay, I'm gonna dedicate a piece of memory just to keep track of my free page. Okay, and that's actually the easiest one, and the one that is implemented. Okay, that's actually the one I was telling you exactly before, right? So here you want to free that piece of memory, and rather than having this, you want to actually coerce them and have that instead, right? If you have a double linked list, it's actually easier. Okay. All right. So we're going to look at 3 placement algorithms, right? There were many that actually were proposed in the literature, but the one that is efficient, let me tell you here, it's actually the buddy systems, and this is the one actually implemented inside Linux. Okay. But just for the sake of it, because this one is not easy to understand, we're going to look at the 2 here, first fit and best fit. There are others here, worst fit and quick fit, but we're not going to look at them in detail, but you have to know they exist. They are not implemented though in any system. Okay. So let's look at first fit and best fit. So first let's start to best fit. So what's the idea? Well, we're going to try to minimize fragmentation by allocating space from a block that leaves the smallest fragment. Okay, so that's kind of like, it sounds like a very, very intuitive idea, right? I want to avoid fragmentation, so when I have a block that I need to allocate, I'm going to try to find a block that actually will leave the least amount of memory fragmented, right? So, okay, so if you do that, no, it's kind of easy, right? So if you have a list of free blocks, I mean, it depends here what kind of data structure you have, right? I'm going to go back to this, kind of, it depends how you implemented it, but assuming that you have a free list, which is like simple, okay, if the heap is a free list of blocks, then you have to go to that list and you have to find what's the best block, right? So it might be like ON every time. Maybe you're going to go to the entire list, or maybe you're going to go there and say you're going to try to find the one that is kind of like good enough. Okay, so you search free for the block or the closest sites to the request, right? So it can be slow, right? Because you have to go through probably the entire list, or at least, you know, a big chunk of the list to find the best fit. Okay. So what can we do better than that? Well, better than that. Well, how about actually picking the first block? You know, regardless of if it's the best one or not, you know, we're still going to go to that list, but we're going to stop. As soon as we find a block that is bigger than the block that we need to allocate, we're going to use it. And it doesn't matter what is going to leave behind as free memory. Okay. So if we do that, you know, it's the same thing, you know, we need a free list. It could be sorted actually, that would be even better, right? So if you sort that list by actually number of free blocks, that's going to be easy, because then you can right away go to the you can find where is the good one, and then you scan the list and you take the first one. Okay, so that's first fit. So let's try to compare them. Let's try to compare best fit and first fit. So here, let's suppose we have let's suppose we have 2 blocks, right? One of 20, one of 50. Okay, and at first here we're going to take one scenario. We need to allocate a 10 and we need to allocate a 20. If we do best fit here, of course, we are going to allocate the 10 inside the 15. Okay, we're going to try to minimize what's left, and what's left here it's going to be 5. And then we're going to allocate the 20 into 20. So here it works. But if we do like a first fit, actually it doesn't work, right? Why? Because, okay, the first block, 10, you're going to put inside the 20. Okay, and it's going to leave a 10. And then you need to allocate 20, but bad luck, you are left with a 10 and a 15. You cannot allocate anything. Okay, malloc returns no. So here you see it doesn't work. But we can find a scenario that actually, that is going to defeat best fit, right? So let's have a scenario when you try to allocate 8, then 12, and then 12. Best fit, first you're going to put 8, you're going to put it inside, inside 15, okay? Because that's going to leave actually 7, okay? And then you're going to allocate 12, okay? So here you're left with 8, but can you allocate the next 12? No, okay? You're stuck. First fit though, you allocate 8 in the first block, and then you allocate 12, actually it takes the entire block, okay? And then you can allocate your 12. So here it works. So which one is best? Well, it's hard to answer, right? But again, I told you, for any algorithm that we can have, we're going to find a scenario that's going to defeat it, make it fragmented, so that we cannot allocate memory, okay? So if we were to compare first fit and best fit, first fit is actually the simplest and actually fastest and most efficient, okay? Because you take the first one that match your need, but it may leave many small fragments, okay? So it's going to leave the memory fragmented. Best fit, it's actually, in terms of storage, is the same as first fit, but it might be a little bit slower than first fit. And guess what? It still have leftover some fragment that tend to be small and unusable. Okay, so which one are best? Actually, you might believe that best fit is best, but actually no, right? First fit it looks even better, right? Because at least it's more efficient in terms of searching for the right memory block. But these two are very kind of like out of the book, very common. We'll see actually that Windows actually use use best fit or first fit. Windows actually use one of them. But we're going to talk about one that is used actually in Linux, and it's called the buddy allocation. And that's kind of a very, very smart idea. Let's try to explain. So on Linux, when you allocate a block, it's not going to allocate the exact block size. It's going to round it to the next, to a power of 2. Right, so you will get, for example, blocks of 8, 16, 32, 64, and so on. Okay, so powers of 2. Why are we doing that? Okay, well, it's easy, right? Because the idea is like we're going to maintain several lists of block size that are 2 kilobytes, 8 kilobytes, 4 kilobytes, 8 kilobytes, and so on and so forth. Okay, so we're going to maintain a list of 3 blocks for each size. And then what? So it looks complicated, but actually it's actually very powerful. Okay. So when you need to allocate a block of a certain size, okay, well, you can basically directly take it from memory. Otherwise, you take a larger block and you divide it until you reach that suitable block. And when you divide a block, for example, imagine you have 64K block, you're still going to divide it in like 2 free blocks of 32. Then you take one of them and you divide it in 2 blocks of 16. And then again, you take this one, you divide it into a block of 8. And that's, for example, that's your block that you allocate if you need 8 kilobytes. Okay. And of course, you put all of these blocks. Here you're going to put this one, this one, this one, these 3. That's it. Inside the list that you have. Okay. I'm going to give you an example. Why this is nice? Because when you, so first of all, it's very easy to find a block, right? Because you have each size, you have a list for each size, so you can directly allocate. It's basically O1, right? You take the head and boom, okay? If you don't have any, okay, fine, you divide it, but it's actually, in log n, okay? So in terms of complexity, it's not very complex. When you free as well, it's actually very simple, right? When you free a block, you check if the body is free. If the body is free, you merge. and then you do it recursively, right? This one here, you check the body, is it free? You merge. And then again, and then you merge, and so on and so forth. What's nice with this 2k to this power of 2 allocation is the address of the body pair only differ by 1 bit. That's why. So if you want to find where is the body, if you want to check, for example, if it's free and you want to cool seed these 2 blocks, you don't need to actually go in through a list or whatever. You need to do a search. You just need to change 1 bit. You test if it is. You actually merge. And merge means you just put it inside the right list. Okay, so it's actually very, very efficient. Let's have a little bit of an example here, because you're going to implement that into project 3. So here, for example, you have a list. So here I have 8 pages. Okay, 8 pages is 2 to the power 3. Okay, so 2 to the power 3 meaning for the k equal 3. So I have a free list, and I'm going to say that I have only one element, and it starts at 0. Okay, it starts at page 0. Okay, fine. Suddenly, I need to allocate 1 page. Okay, so 2 to the power 0. I need to allocate 1 page. Where am I going to allocate it? I told you, right? We take this big chunk here, okay, because that's the one I have free. It's not what I want because I'm looking at a free list of 0, but there is none. So I'm going to take this one and divide it. Divide it in 2 first, and then take the first part, divide it in 2 again, and then take the first part again and divide it in 1. So if I do that, I'm going to allocate the first thing here. His body is going to be here, and so I'm going to obtain that. So now I have a big free list that starts at 4, which is a power of 2. Okay, that's 4 pages here. Okay, a free list power of 2 start at 4. And then I have a free list here of power of 1, that's the green one here, and then starts at 2, page 2. Okay. And then I have this one that is free here, okay, and starts at 1. Okay, and this one is not free. All right, so let's try to allocate again. Now I need to allocate a block of 2 pages. Okay, so if I try to allocate 4 pages, okay, 2 to the power 2, 4 pages. So 4 pages here, I just need to look into my list here. Oh, wait a second. I have 1, it starts at 4. Okay, fine. I'm going to allocate this one. What's left here is these 2 things. Okay, meaning the green here and the yellow. Okay, let's start to free stuff. I'm freeing P1. So P1 I'm freeing here. So if I free this one, I could actually just, what I could do at first is like, I'm going to put it inside free list 0, and I'm going to have 0 and 1. But instead of doing that, what I'm going to do is like, I'm going to check the body, okay? And if the body is free, yes, it's actually in the list, I'm going to merge them. And so if I merge them, I'm going to insert them into the list free 1, 2. But here I'm going to do the same thing, right? It's recursive. Wait a second. Is the body of this block here is free? And yes, it is, okay? So we merge them. And certainly now, we have freed it. This is not free. The body is not free. So we are left with that. Now we have a free list of 2, 0. You see, it's very compact. And finally, if we free P2, okay, same thing. We merge the one that we free with the body. Right? Very simple. So that's how it works. So what's the advantage of that? Well, it's fast. Okay, to allocate, it's very fast. You take the head of the corresponding list. Merge, it's also very fast. Okay, when you want to free memory, you just check the body and then you merge them if it's free. You do that recursively, but basically this is in n log n. Okay, so you don't iterate to an entire free list. Okay, so and you don't iterate because actually it's in you just need to flip bits. You avoid external fragmentation. Okay, so because you always you always have like 2 to the power n blocks available. Okay, you might have internal fragmentation. What does it mean? You allocate something that is you allocate, for example, 100 kilobit. The system is going to give you 128, right? And you see that on Linux actually. if you allocate an array of like 100 chars, it's going to give you actually 128. Okay, whether you want it or not. And then you keep the physical page contiguous. Okay, so this is actually one of the best algorithms out there, and it's used by Linux and FreeBSD. Okay. All right, so that was to allocate free memory. Now, so again, when I was allocating free memory here, sorry, there was a question here. Let's see. I'm confused about the colors. The colors are just meant there to differentiate the different blocks, right? But I agree. Maybe I could redo these drawings here and change the colors and use one color when it's allocated, one color when it's not allocated, and that's going to be more clear. Yeah. Okay. But Jackson is right here. So when you use freelist3 it means there's a free chunk of 2 to the power 3 starting at next 0. Correct. Okay, that's the most important here. Okay, the colors here is just like to distinguish the blocks. Okay, all right. But yeah, maybe I can redo this one. Okay, so now let's talk about. We are still so here we're going to go back to paging. Okay. And we're going to go back to this thing here. So what was that? I showed you that last week. So what's the idea? The idea is as follows. Again, imagine you can store everything in physical memory. That's fine. So you have everything in physical memory, and then you have one virtual kind of memory per process. Meaning every process will have one page table that maps its virtual addresses to physical address, okay, into memory. So here again, that's the drawings, right? The physical memory contains, everything, okay, all of the data needed by all the processes, okay, and each process has a page table, and at some point the process needs to access page, okay, so it needs to access a page, and then the page is going to translate to the physical memory to get back what it needs. But at some point, if we are running out of memory, what's good is actually to swap. Swap means we're going to page out, we're going to, outsource the storage of a page from the physical memory to the disk. Okay, so, and that's going to free stuff. But what if actually here a process tried to reference a page that does not exist in physical memory? Okay, because actually we put it on the disk. What's going to happen here, it's called a page fault. Page fault, what do we do? Well, so we know that there's a page fault because there's going to be an invalid bit that is set. If we see this invalid bit, we're going to actually send a page trap. And who does that, by the way? The MMU, okay? The memory management unit. It's going to send a trap to the operating system. Trap understand an interrupt, a software interrupt. It sends an interrupt saying, hey, I tried to access something in physical memory, it's not there. Okay, fine. Here you have an interrupt handler kicking in. The handler, what it does, it goes to the disk, fetch the page that is required, put it back in memory, okay? So you can put back somewhere, okay, in memory, and then update the page table of the process here, and then give the hands back to the process, and the process again try to fetch the page, and now it works. Okay, so that was the story I told you last week. Okay, and this story works. The detail that we're going to look at today is the following. Okay, so here, when the operating system is going to fetch the page from the disk and put it back in physical memory, wait a second. We are doing that because the physical memory is full. So here, where do we put it if it's full? We need to evict a page. We need to kick out another page. Which one are we kicking out? Okay, and that's going to be the big question here. So which page should we kick out? And by the way, by kicking out, it means actually we're going to swap it to the disk, right? We're not going to just delete it, right? We're going to put it back to the disk because maybe some process will need it at some point. Okay, so it would be good if it's a page that has not been used recently, or it's actually even better. It would be nice if it's a page that is not going to be used anymore. okay? Because that means that, nobody will ask for it, okay? So here we're going to try to minimize the page fault, basically. So again, that's kind of a summary of what I just said. What happened when there's a page fault? The OS takes over, okay? There was a trap, the OS takes over, and then it's going to load the page frame from the disk to the physical memory, okay? What if there is no physical memory available? Or actually, the process has reached its limit in terms of maximum page frame allowed. Okay, I'm put that here because that's actually how Windows work. Linux doesn't work like that, but Windows does that. Okay, so here it doesn't matter. Either actually the memory is full, or actually there is some kind of a limit put on the process that says, hey, you cannot have more than X pages. So in that case, the OS must evict an existing frame, okay, and swap it and replace it with a new one. Okay, but how do we determine which page frame to evict, right? Because again, the idea is like we want to minimize page fault, because page fault means the OS needs to do something, meaning it takes time. Okay, so we want to minimize that. So again, we're going to have some kind of an algorithm to minimize page fault that is going to determine which page to evict, right? So that's the idea. All right, so we're going to look at several algorithms. So basically we're going to look at three. One is FIFO, first in, first out. Basically here, the last page that came in, we're going to evict, we're going to kick it out first, okay? We're going to look at the list, the last recently used, and another one called second chance, okay? And we're going to see that. Again, when you try to evaluate those algorithms, which one is better? Well, it's hard to tell, right? Because it's a little bit like fragmentation. You're going to find a sequence of events where each algorithm is going to not perform well, okay? But kind of to compare them, what you can do is like, you can take a long or even random kind of stream of page access and try to, for each of them, try to actually compute the rate of page fault and see in average, which one perform better, okay? And we will see that there are some algorithms here that do perform better. Okay, so let's try to do that. So here, I'm going to show you how this algorithm perform on a sequence of page access. Okay, what do I mean by a sequence of page access? Well, let's look into here. Okay, let's imagine the following. So here it's important that you understand what this array means, okay? So here we have an algorithm, first in, first out. What's the idea? We're going to evict the oldest page in the system, okay? How many physical pages do we have in memory? 3. Okay, it's a very, very small memory. That's just for the example. Okay, we have 3 pages there. But how many pages are there? Well, more than 3, actually. Okay, and that's why some of them are on the disk. Let's assume here I can have 5. Okay, so that's why here my program can access, page 1, page 2, page 3, page 4, but even page 5 and so on and so forth, right? And we have a sequence of things. So imagine here the program starts with 1, 2, 3, 4, and then 1 again, 2, and then 5, and then 1, 2 again, 3, 4, and 5. Okay, that's a sequence. And here, to access those pages, these pages needs to be in my physical memory. But my physical memory has only 3 slots. Now I'm going to call P0, P1, and P2. Okay? So how does it work? Well, let's start. At first we start, and we're going to call that a cold start, meaning there is nothing in memory. Nothing. Okay? So there is nothing in memory, meaning I need page 1. Is the page 1 in memory? No. It's a miss. Miss means page fault. It's a page fault, so I'm going to swap it. I'm going to get it from the disk, and I'm going to put it in the first slot, because the first slot is free. So I'm going to put 1 here. So inside my slot 0, okay, my page 0, I have my page 1. Okay, frame 1 if you want. All right, so I have 1 here. So I do it again, right? Now 2 is a miss. Okay, fine. I load 2 and I put it into P1. 3 is a miss. Okay, fine. Now it's inside P3. So here, after this line here, my memory is full. Meaning, if I need another page, something that is not 1, 2, or 3, because if I need 1, 2, or 3, they are there. So that's fine. But if I need something else, I will have to kick out a page. So here, that's what's happening. 4, I need to kick out a page. So which page am I going to kick out? Well, we have to go to the algorithm. The algorithm says first in, first out. Who was first in? First in was actually 1 on slot page 0. So I'm going to kick out this one. I'm going to evict 1 and I'm going to put 4 instead. Now I have 4 and I have still 2 and 3. Guess what? Now we need 1. Again, it's a miss. Miss means, okay, fine. We're going to evict the second oldest one, and here the oldest one was 2. So now I kick out 2, I put 1 instead, and I still have 4 and 3. Okay, so you understand how it's going here. Again, here I need 2. Okay, bad luck, I just evicted it, but that's the algorithm. Same thing, now I'm going to kick out the oldest one, which is 3. I have 4, 1, and 2. Okay. Same thing with 5. Again, now it's a page fault. I need to evict 4. Now 4 has been the oldest one, and I put 5. Here, I need 1. And finally, it's a hit. Okay, finally, I have one page that I don't need to get from the disk. It's already there in my physical memory. Okay, good. When it's a hit, I do nothing. I just, okay, fine. I access it right away. Oh, I need 2 again. That's a hit. Perfect. Okay, fine. And then I need 3. It's a miss. Okay, 3. What was my oldest one? It was actually 1 here. You see, longest stretch. So I evict 3. I evict 1. Sorry, I put 3 instead, and so on. I need a 4. It's again a miss. A miss. I'm going to evict 2, and I'm going to put 4 instead. And then finally, I need 5. 5. Oh, great. It's a hit. Okay. Here, how many miss did I have? Okay, I had 9 miss. Okay, you might say, no, the first 3, of course, they were miss, but let's count for all of them. I had 9 miss in total and 3 hit. Okay. Let's keep the same algorithm, but here's the question. If we have more physical memory, does it mean fewer page fault? Okay? Intuitively, you're going to say, yeah, sorry, a question here. A miss is a page fault. Yes. Okay, a miss is a page fault. So if we have more physical memory, are we going to have fewer miss? Okay? Intuitively, we're going to say yes, right? I mean, if we have more, of course we're going to store more stuff. And if we store more stuff, chances are that we're going to have more, we're going to have what you need when you request it. Well, let's look at it. I'm going to take the same sequence and I'm going to add just 1 slot here. Okay? And I'm going to run the same algorithm. So here, maybe I'm not going to spend too much time running this algorithm. But here's the thing. If you run it and you count the number of misses, strangely, I have 10 miss with 4 physical pages. I had only 9 with 3 physical pages. That makes no sense. Okay, but actually it's correct, right? I mean, you can double check my algorithm and so on. I have more misses, although I have more memory. It's weird. This is called the Berardi's anomaly, right? So more physical memory doesn't always mean fewer fault. Okay, here it just means that actually my algorithm is not that great, and it creates this kind of anomaly here where actually sometimes having more memory is actually slowing down things. Okay, which is kind of nonsense. All right, so Berardi, okay, the guy who basically find out that FIFO was not great, proposed actually the optimal algorithm. Okay, the optimal, which is what is the algorithm that is going to minimize the number of fault. Okay, you cannot avoid having faults, right? But what's the minimum one? On this sequence, the idea is the following. What if you knew the future? Okay, you can look into the future. So here, if you can look at the future, let's see. I'm going to go here and, for example, I load 1, 2, 3, and here I have a miss, right? Actually, I forgot to put which one. Because I have 4 slots, right? So here I put these 4 slots. By the way, this is, so far, it looks like exactly the same as the FIFO with 4 physical page, right? So miss, 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 miss. Hit, hit. And then let's see. Now we're gonna have a miss again for 5. Which one are we gonna evict? Well, here we're gonna look at the future, and the future tells us, hey, you're gonna need 1, 2, and 3. Okay, if I'm going to need 1, 2, and 3, I'm not going to kick them out. I'm going to keep them. And instead, I'm going to have 4. Okay? As a result, well, oh, sorry. That's not the one. Okay. As a result, okay, the next 3 are going to be hit. Okay, great. So the next 3 are going to be hit. Of course, when I'm going to ask 4, it's going to be a miss. I'm going to look into the future. Here, the future tells me I only need 5, okay, but you know, I could have evicted 2 or 3. Doesn't matter. But the future tells me I need 5, so I'm going to keep 5, and I'm going to evict 1. Here, I'm going to put 4. Total here, it's going to be 6 misses. You cannot go below actually 6 misses. You try to find whatever thing. This is the optimal one. Okay, you cannot go below 6 misses. All right, but Belady's algorithm, it's nice. It's impossible to implement. When I say impossible, it's impossible. Why? So actually, Belady has been proven to be the optimal algorithm, right? It's really optimal. But the problem, it's impossible to predict the future. Why? Because you have a live system. You don't know which page are going to be accessed in the future. It depends what the program does, right? So you cannot know that in advance. If you don't know that, you cannot make any prediction. Okay, so you don't have a crystal ball to look into the future, basically. That's what it says here. Okay, but still, Belady's algorithm is still useful because now if we come up with any algorithm, we can compare it with Belady's algorithm to say, okay, how much room of improvement do I have? Okay, there is always a threshold I cannot go below. Okay, and that's actually going to be Belady's algorithm. Here, it means I cannot go below 6. Okay, but right now, at best, I was at 9. Okay, actually 10, if I consider 4 physical page. Can I improve that? Well, we will. One of the good algorithm, okay, is called last recently used. What's the idea here? Instead of evicting the page that came first, I'm gonna evict the page that has not been used the longest in the past. Okay, so Belady's, you look into the future. Here with RRU, I'm gonna look in the past. I can do that, right? I know the past. So here, what does it mean? Okay, beginning, it's the same. 1, 2, 3, 4, miss, 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 and then 1, 2, hit. And then I have 5 here. So when I have 5, I'm going to look in the past and I'm going to say, oh, in the past, I need 2, 1, and 4. So I'm going to keep 2, 1, and 4 just in case I need them again. So here, it means I am going to evict 3. And 3, you see, is the one that was last recently used. Okay, so I'm going to evict 3 and I'm going to put 5 instead. As a result, hit. Okay, that was lucky. Maybe it could have been something else, right? I don't know what's going to come in the future, but here it turns out actually I had two hits. And then I have a miss again, okay, for 3. Miss, I'm going to look at the past, 2, 1, and 5. I'm going to keep 2, 1, and 5, so I'm going to keep 2, 1, and 5. So I'm going to evict the 4 slots here. Okay, and then again I have miss. Total 8 misses. It's actually better than my 10, right? It's not 6 yet, but it's somehow actually in the middle. This algorithm performed better than FIFO. Okay, and that's true actually. So it's true in this example, but it's true in average. Actually, RRU performs better than FIFO. All right, so how do we implement RRU? Well, idea number 1, I can stamp the page with the timer value, right? I can say, for example, this one was used 3 access ago, right? It doesn't have to be a physical time with a clock and so on, right? But you can say, I accessed this one 4 access ago, right? So stamp the PT with the timer value. On miss, scan the page table to find the oldest value and so on. If you do that, that would double the memory traffic. Why? Because every time you have a miss, you need to find, you need to look at all of these values and compare them, right? It's going to be expensive. What you can do also, you can keep a double linked list of page. Okay, on access you move the page to the tail. On remove on miss you remove the head, right? Because if you keep always the last recently used on the head, okay, you know that when you have a miss, you can kick out the head. Okay, so on access, you move the page to the tail, meaning you put it at the end. So chances are, this one is not going to be kicked out. Okay, that's very kind of idea, but again, you have a double linked list. It is expensive. Okay, and on every access you have to move the list and so on and so forth. It is expensive. So instead we need to approximate RRU. So RRU again is not implemented in systems. What we have is something we call second chance. So what's second chance? Second chance, it's going to use something we call an access bit. If you remember last week, I told you, right, inside our page table, we can store information about when a page was accessed, and it's just one bit. Okay, well, let's see how we're going to use that. So here we're going to use it that way. Okay, so FIFO, second chance is actually like FIFO. Okay, but so meaning we're going to look at the oldest one. I mean the one that was kind of that came first. But instead we are also gonna mark the ones that was recently used. So let's see how it works. Beginning, miss, that's normal, that's a cold start. And then one, there is a hit. If there is a hit, we're gonna turn on the access bit. And here I put some kind of a star on the one. Okay, so I turn on the access bit. And then again I have a hit. Okay, so I'm gonna put the access bit of 2 here. And then I have a miss. So if I have a miss, I'm gonna say, okay, it's gonna be like FIFO, which is what is the one that came first. The one that came first is a 1. But 1 has a access bit on. So okay, so what I'm gonna say is the following. I'm gonna give 1 a second chance. That's why this algorithm is called second chance. I'm gonna give 1 a second chance. I'm gonna turn off the bit and I'm gonna say, okay, for this time, you stay here. And then what's the other longest one? It's actually 2. But 2 again has a bit. Okay, fine. I'm going to give you again a second chance. 3, no access bit, no second chance. I kick you out. Okay, and then I continue. Okay, I have a hit. Okay, again, I access this one. Hit, I'm going to access this one. Miss, I need to replace. Okay, which one do I kick out? 1 is actually the longest. You see, it has very longer strike, but again, it has the access bit here, right? This one has also an access bit, so I'm going to give it a second chance. Here I'm going to evict 5. Sorry, now it's actually 4, the longest one. I'm going to evict 4, right? 5 has been there for a less long time. So I'm going to kick out this one, okay? Same thing now with a miss when I have 4, okay? So here, actually this is wrong, because here I'm going to kick out 1. Okay, I got confused here. I should kick out 1 because now the access bit of this one is actually, this access bit should be disabled. Here I should kick out 1, okay? And then I'm going to kick out 2. Okay, there is a problem here in this slide. Sorry, I'm going to change that. Okay, so let's see. Question: when is this supposed to be turned to be evicted, but it has an access bit? Do you remove the access bit? Yes, exactly. You turn it off, meaning you put it to 0. Turn it off means put it to 0. Okay. Actually, I have the algorithm here. Let me explain. So here I have the algorithm because you will have to implement that for project 3. So I have kind of the algorithm in better layout than this array. But so here the access bit is supported by most hardware, by the way. So it's automatic. You have nothing to do. The access bit is going to be turned on automatically on access. So you keep a linked list of pages with 2 pointers, a head and a tail. Okay. On hit, what you do is like you turn the access bit to 1. Okay. That's it. On miss, what you do is like you look at the head, and while the head access bit is 1, you move it to the tail. Okay, you turn it to 0, by the way, and you move it to the tail. You say, okay, haha, I was about to kick you out, but you are getting a second chance. I move you out to the back, but now with the access bit of 0. Okay, and as soon as you find the head with access bit being 0, you swap. Okay, you swap the head and you move it to the tail. Okay, so here this has good performances, but the problem is like on every miss you have to rotate stuff. You have to move stuff from the head to the tail. Okay. Oh, and by the way, if I look at my algorithm, this is actually correct here. Why? Because here my head is going to be on 5. Well, let's see. Actually, it is correct. The one I evicted 4. So my head is here. So my head is here. Yeah. Then I move this one, and that's going to be my longest one. And I'm going to kick out this one. Yeah. Okay. So actually, no, the algorithm works. I was wrong. This is correct. Okay. Because my head is here. I move back to here, clear the bit, and then move 4. Okay. I evict 5 to put 4 here. And here, same thing. Now my head is actually here, and that's the one I'm going to evict. Okay. All good. It's working. All right. So here, it's good, but it requires moving pages on every miss. Can we do better? Yes, we can do better. There is a version of second chance called the clock algorithm. And that's the one that you hear a lot because this one is implemented actually on Linux. The clock algorithm is as follows. Still the same, you still have an access bit, but this time you will have a circular linked list. Okay, you have done that in BO9, you basically circle through your list. And now you have only one pointer. No need to have head and tail, only one pointer that you call the hand. It's the hand of the clock. What do? On hit, same as before, you turn the access page to 1. You do nothing with the linked list. On miss, you do the following. While the hand access bit is 1, you set it to 0, and then you move to next. Okay, so you see here, this is faster than before because you don't need to rotate stuff. You just move the pointer. Okay, and you know it's cheaper. So you just move the pointer. And then, until you find what? Until you find the hand points to an element where the access bit is 0. And when you find this one, it's the one that you should swap. Okay? So here, this one actually is better than the FIFO-like second chance. Okay, the FIFO-like is the one I had before. Again, these two variants are equivalent. They both implement the second chance algorithm. They will both have the same result like I have here on this array, right? They're just variant. But now, this one is actually, the clock algorithm is actually the one that is faster because you don't have to rotate stuff. Okay, you move only the hand of the clock. Okay, so that's actually better. There are other replacement algorithm. Okay, guess what? There is actually the one that is called random. Okay, you select one at random. You might think that this is chaos and this is at bad performance. Actually, it's not. It has actually good performance. Okay, not of course as good as the second chance, but better than actually FIFO. Okay, it avoids Beladi's anomaly, for example. Okay, there is also another one called LFU as opposed to LRU, which is the least frequently used. Okay, so you're going to look at the past and you're going to kind of give, you're going to look at how many times a page has been accessed. Okay, and you will kick out the least frequently used. Okay, but same thing. This one is like LRU. It's hard actually to implement. Okay. And there is another one called MFU, most frequently used, okay, but it's kind of dependent of LFU, right? It's kind of they're equivalent. But neither LFU or MFU are commonly used because they are not very efficient. Okay, the one we use actually is clock algorithm. Okay. All right. Any question about this part? No? Okay. So it looks like I'm going to finish early. So let me explain what's the working set model, and then we're going to be done. So here, before I move into that, let me set the picture again. Again, what do we have? We have multi-processor, or multi-threads. Okay, all these threads, they have their own virtual memory, meaning they have their own page table, and they all use the physical memory. So the physical memory stores pages of all of this process. When the memory is full, we have an algorithm that I just talked about, right? An algorithm to actually kick out the least recently, to kick out the best page to swap it to memory, right? To make room for to page in the one that was swapped. So here, this algorithm might kick out a page of another process, right? No problem. Okay, so you're running GCC, and GCC needs a page that was used by your code editor. Okay, used by, I don't know, Vim, for example, or Emacs or whatever, right? So you can do that. So meaning they're all going to compete and they're going to kick out the process of each other. Why not? Or we can be more restrictive. For example, you are going to run this algorithm, but only on the pages for the same process. Meaning we're going to give you a maximum page and that's it, right? So here I was talking about 4. Either it's 4 because it's the entire memory, or it's 4 because it's all the memory page that you are allocated to one process. So you see here, what I'm talking about is like two different choices. These two choices, we call that fixed space algorithms and variable space algorithms. So here the idea is like, are you going to determine how much memory you give to each process? Okay, so here, if it's fixed, yes, you give each process a limit number of page they can use. If they reach the limit, okay, you replace its own pages. Okay, this is called local replacement. Okay, here, if you do that, the problem is like, how many pages do you allocate per process? If it's fixed, you give all of them the same thing. Some process needs more memory than others. Okay, meaning some process will do fine because they don't need that much memory. Others will do they will suffer. Okay, so it looks like it's not a great choice, but actually that's how some systems work. Or it's a variable, and you're going to change that thing. Okay, the process grows and shrinks dynamically. Okay, so here you're going to allocate the page. But if you do that, one process can ruin it for the rest, right? If one process keeps growing and growing and growing and needs more page, and the system allocates more page, it means the others will have less, and we need to do swapping a lot, right? Which one is better? Well, it's hard to tell. Okay, and actually Linux and Windows have chosen different options. So how do we evaluate that? For that, we can talk about something we call the working set model. What's the working set model? Is like, we're going to try to profile how much memory an application needs. We're going to try to measure it. And how are we going to measure it? Well, we're going to have something we call a working set. What's a working set? You fix a time. So for example, you're going to say, it's going to be in terms of like, so it's going to be measured in page ref. So I'm going to look at, the last 10 page ref. Okay, page access. And here, throughout this page access, I'm gonna look at, so that's why there's an interval, right? Interval between now and the 10 pages ago, okay? And I'm gonna look at how many pages were accessed, okay? At max, it's gonna be 10, of course. But at the minimum can be actually 1, right? If you access always the same page, you have only 1 page in the set. And like this, you're going to try to actually measure how much memory you need, right? So a page in the working set, only if it was referenced in the last W reference. That's the idea. So if you do that, okay, so here, basically for every time interval, you're going to have a collection of pages. So now what you can do is like actually you can count the number of pages. So this is called the working set size. So here, you're going to count the number of unique pages in the working set for a given interval. Okay? And here, of course, during a period of poor locality, meaning here, the program needs a lot of pages. Okay? Oh, so there's a question, why it's T plus W? No, because you look in the past. The idea is like, you're going to try to take a snapshot where you are right now to the past. Okay? I mean, it's the same. You can think of, really, you can also think about the future, right? But the future is hard to predict. So you can always do that calculation after the fact, right? You can record everything and then look at it. But the idea is like, can we have a snapshot at instant and right now, and we're going to look at the past because we don't know what the future is going to be about, right? So here If this number is high, meaning the working set size is high, it means that many pages were accessed. And here it means that you have poor locality, right? Because you reference more page than you have, right? If you have good locality, all the operations you would do would be in the same page, okay, or very close. So during that period of time, the working set size is larger, okay? So ideally, you want the working set process to prevent heavy page fault, right? So you can have a parameter to actually only count the page fault, okay? And you can look at actually the page fault. So here, just to show you, for example, you have some profiler that do that on programs, okay? So here, for example, if I profile GCC, you're going to see that. So here, for example, you can see that here at this time, okay, there were more than 71 page, 71, 70 something, 71, 72 page accessed in the time T. Okay, so here, it's a certain time, I don't know which one, but here at this point, it means, I have used a lot of pages. So I was doing something that requires, a lot of access to a lot of memory. And then suddenly it slows down, okay? Why? Because maybe, I'm still doing computation, but maybe here I'm always accessing the same page. It doesn't mean I'm not working. I can do some kind of, operations, intensive math and so on, but I'm always accessing the same page, okay? So here, that's in average. So you might say, I have some peaks here, but I can calculate an average and so on of how much memory I need for GCC. Okay, knowing that, because I have peaks, it will be better if I allocate more than 80 pages here. Okay, so that's the idea of profiling. Again, can you use this working set to predict how much a process needs in the future? Well, no. Okay, because first of all, it's hard to determine W, right? Because what you have here is a picture of the past. You don't have a picture of the future. Okay, so here you can see that it's not because you reach that point that you say, oh, it means I need more memory in the future. Actually, no, look, actually I needed less memory in the future, right? So it's a good information to have, but you cannot use that to actually know how much to allocate. Okay, but it's still good abstraction. Okay, when people ask, for example, how much memory Firefox needs, or how much this process consumes memory and so on, they talk in terms of working set. Okay, and you have a max and average and so on. So of course it's not one answer, but you can have some kind of a profile that tells you, hey, here is the profile of that application. Okay, I mean, given the input I give it, right? Of course. So something you can do instead, and that's actually Windows does that. You can look at the frequency of page fault. Okay, and you can use that as an indicator. Actually, Windows does that. So instead, you look at the page fault since the beginning of the process, actually. So you execute the process, and then you start counting how many page faults you have. You have some kind of a threshold, okay, that you determine, beforehand or in ad hoc fashion, okay. And if the page fault is above this threshold, okay, it means that you have too many page faults. So you're going to give more memory to avoid faulting. Okay, or if a page fault is actually lower than this threshold, it means you can take away memory, right? So you're going to try to kind of average the page fault of every program, okay, by giving more memory and so on, right? So Windows actually does that, okay? So it tries to adjust the memory to give a process like this dynamically, okay? At some point, what you might have is something called trashing. It's happened when you have an overcommitted system, meaning you are running out of memory. That's what it means, right? So basically, you swap a lot of stuff on the disk. By the way, this happens on your computer. If your computer is working and you hear, for example, a lot of disk access going on, and your computer is slow, it probably means that your memory is actually swapping a lot. Okay, it's swapping and putting up stuff to the disk. Why it keeps doing that? Don't forget, right? We have threads going in parallel, concurrently, and they will all get the CPU, and when they get the CPU, they will access memory. If the memory is not there, you will swap. And then you move to the next process. And the next process, if you don't have enough memory, it might actually use the memory slot of the process before, and so on, right? When you rotate, it's actually, you spend your time basically swapping. That's bad. It can happen for two things. Either you have a bad page replacement algorithm, okay? But again, if you use Linux or Windows, they believe it's the best one, right? Most likely you don't have enough physical memory, okay? Or too many process, right? But that's what's happening. So let's talk, to conclude, I'm going to talk a little bit about what's going on Windows and Linux. They have two different strategies, okay? So Windows, it's a local page replacement, okay? Again, local here, local page replacement, oops. So, sorry. It means that each process is giving a page limit, okay? And actually here it's, there is a page limit. Here, you see, process start with a default of 50 pages. Okay, so we give a page limit, and then Windows XP try to monitor the page fault and adjust the working size. That's exactly what I was telling you here, right? You try to look at the page fault. Okay, everybody start with 50, and then depending on the page fault, it's going to try to adjust that number. Okay, something interesting. You use a FIFO, okay, a per process FIFO, and that's actually probably because it's fast. It's actually efficient. Okay, for Windows. So of course, you might stole pages from other process. Okay, that's part of the game. And also something that Windows tries to do is that when it loads a page in memory, it doesn't only load that page. It tries to load the adjacent page. Okay, I was telling you that when I was talking about paging. Windows does that. So, if you need a page, chances are that you will need also the data that is contained to the page that are next to those ones. So Windows does that. Rather than loading only one page, it loads actually a cluster of page on a page fault. Okay, that's how Windows manages memory. Linux, completely different. This time we have a global replacement. Okay, so here there is no minimum page allocated and so on. It's your turn. You need a page. Tell me, I'm gonna kick out other page. Okay, it uses a clock algorithm. Okay, the one I was telling you, with the second chance and so on. But there is not only one bit. This time they have like some kind of a counter. Okay, and the page age every time you pass the clock. Okay, so it's more complicated than what I told you. And here, the pages that are used for longer time will eventually get to 0 and will be replaced. This is a little bit like between RRU and then the clock algorithm, right? It's a kind of something in between. And that's how Linux used the page. Which one is better? It's hard to tell, right? Why did they have two different strategies? Most likely, you have to remember the following, right? Windows, it's mostly desktop computers, meaning there's going to be users and so on and so forth, right? It's a different type of applications that when you have a Linux, which is mostly used for servers, and so they're going to do different jobs. So maybe, actually, I don't know, but most probably these two different type of usage have shaped Linux and Windows differently. Okay, that's why they still believe that their strategy is still the best. Okay, and they're probably right. Okay, actually, for the kind of usage they have. Okay. Questions? Can you explain when they get to 0? So here, so what they do is like they give. So it's not like you don't have a second chance as it's not 1 or 0. Okay, they're gonna tell you have been accessed. I'm gonna give you maybe 10 second chance. Okay, so it's not one bit. And every time the page age is like, okay, it was 10, now it's going to be 9, now it's going to be 8, now it's going to be 6, and so on, until actually it reaches 0, and when you reach 0, you've been kicked out. Okay, so that's the idea. It's more than just one bit. Okay, we'll give you more than just 1 second chance. Because again, process are likely to reuse the page that I've used in the past, so if a page is accessed, it's probably going to be used later. That's it. Okay. So let's see. Maybe I'm going to stay around a little bit. If you have questions about memory access. And by the way, most of this stuff you're going to implement into Project 3. Okay. Project 2 talks about virtual memory already. Okay. So there is a little bit of paging, management, and so on. But mostly it's to use the virtual memory, not really to manage it. All the management is going to be done in Project 3. Okay. Project 2 is about system calls at first. Any questions? I don't know if it's a question, if you're still typing. When you free twice, well, basically, I mean, this is typical error, right? When you free twice, you cannot free something that has been already freed, right? So if you free twice, what's happening is like, you're basically saying, hey, can you take this block and then merge it with the rest, right? And okay, there is going to be a system call. The system call tries to do that. And then what? Well, it says, I cannot find this block. Sorry, it's not there. And that's why you get the segmentation fault. Can you go over the linked list of block part again? Oh, wait, I have many linked lists. So you have to tell me a little bit which algorithm. Are we talking about page replacement? Or are we talking about allocating free memory? Allocating free memory, you're not going to... are you going to do that in Project 2? I forgot. I don't think so. I think it's going to be in Project 3. But the one I talked about, which is you're going to have to implement, let's see. The one you're going to have to implement for sure, it's the page replacement algorithm. You have to implement second chance. And you're going to implement the clock algorithm. So if you want, I can re-explain this one. So let me re-explain this one quickly. So here, second chance is the idea of like, okay, it's like RRU. We're going to look in the past, but it's time consuming to really look at, the last one that were used and so on, right? We need to make a decision right away, very quickly. So instead, what we're going to use is this access bit here. And still, we're going to use FIFO, okay? Or some kind of a FIFO, okay? Why? Because it's actually quite fast, right? So here, the idea is the following. When you have a hit on something that is already in your, here, when you do a hit on a page that is already inside your physical memory, okay? You have nothing to do. The only thing, you're going to turn on the access bit. So that's why here what I do is like I turn on the access bit and I put a star. Okay? And here same thing. So on 2 I'm going to turn on the access bit. When am I going to turn it off? Well, I'm going to turn it off, so here I have, well actually it's the same, right? Clock or whatever. I'm going to look at my head, okay, or the hand. And if it's 1, okay, maybe here I should say the following. The idea here is that you will always point, you will keep a pointer to the one that you're gonna evict, right? So you keep a pointer. So here, for example, I keep a pointer. So after this point here, I keep a pointer on 1, right? Because that's the next one I'm gonna evict, right? But here, when it's time to evict it, I'm going to say, aha, okay, I was about to kick you out, but guess what? You have a second chance bit, okay? I'm going to give you a second chance. I'm going to move to the next one. Can I move 2? No, it has also second chance. Okay, then I'm going to move to the next one. And finally, I'm going to evict 5. I'm going to evict 5, and now the pointer is going to be on 4. Okay? That's why the next time around I have a miss, okay? I'm going to replace 4. Okay. So here, that's what I mean by that. Okay. So, you know, if they have accessibility at 1, you're not going to kick them out. You give them a second chance. Okay. But you put them in at the back of the tail, or even better here, you do nothing with the clock algorithm, and you move to the next page. Okay. And finally, when you find one that is 0 and, you know, say, no, too bad, it's, you know, you don't have a second chance, now I'm going to kick you out. That's the idea of this algorithm. Okay, the question you are mentioning is about security here. Okay, this is out of the scope of this class. If you ask me the question in the fall in D27, we will look into it. Okay, but I think it's out of the scope of this class. Good. Okay, any other question? All right, office hours during reading week. I don't know about the TAs. For sure, I'm gonna have more office hours. Okay, so I will send an email on Piazza. First, I'm gonna ask the TA to see if they are available. We're gonna try to have as much as possible as office hours to help you with the project too. Okay, so before the end of the week, I will send a Piazza post telling you about the next 2 weeks how we're gonna do that. Okay. Okay, question, why we have page fault? Again, this goes back to paging I did last week. Actually, here I can just go back to that. It's important to understand why we have page fault. So why do we have page fault? First of all, you might not have page fault at all, right? If you have large enough memory and, you know, all the process together, they are running and they can use the physical memory, okay, because you have, I don't know, 8 gigabits of RAM and all of your process, including the OS and so on, they don't take up to 8 gigabits, okay, you will never have a page fault. Everything is in memory, meaning every time you ask a page, I can tell you which page it is in physical memory, okay? So there will be no problem if you have enough memory. But guess what? That's the thing I was telling you last week. We have this magic thing to allow you to write programs that use more memory than you have. Or even like other programs together can use more memory than you have on your computer. And how do we do that? Magic, well, we're going to also use the disk. Okay? Meaning we're going to store information that you have in memory on the disk. Okay, because the disk is huge, right? Usually it's like gigabytes or terabytes now. So how does it work? Well, if a page is on the disk, okay, because it has been kicked out, okay, and that goes back to what I talked about today about which one to kick out. Well, here, when you try to load, so when a program tries to load something from memory, it always loads from memory, right? But what if it's not in memory? So if it's not in memory, it knows because of the page table that it's not there because there is an invalid. If there is an invalid, it says, okay, it's not in memory. If it's not in memory, there is nothing we can do, right? We cannot actually fetch the page. So here we send a trap. Trap means an interrupt, okay? And tell the operating system, hey, I need a page that is not in memory. Okay, fine. I'm going to fetch the page from memory, put it back in the physical memory somewhere. Okay, maybe here in the process, I need to kick out the page, okay, some pages. I put it back there, I update the page table, and then resume the program, so now you can access it. Okay, that's the idea. That's why. But again, if you have too much memory, I mean, if you have enough memory and don't need to swap, no problem. Any other question? All right, if no question, it's important. If you have time today, take a look at project 2. Take a look at the code and start actually have questions. Don't rush it, take your time and so on. Start playing with it, start to actually see what's the system call, what's happening, and so on and so forth. If you have questions, tomorrow during office hours, okay, I will answer. But again, it's important that you have this system call set up by the end of this week, okay? Because it's a big project, you have a lot of things to do, and this one is the hardest part. Once you are done with this part, the rest is actually easier. Okay? Again, don't work in the dark. Debug. Okay? Print stuff or use GB, whatever you want, but you should know when there is a context switch. You should know when there is an interrupt. Okay? And you should know when it happened. Okay? Otherwise, you will not understand why you have weird result, which is most likely a race condition. Okay? All right. Good luck with project 2. Talk to you in office hours or and so on. But for the lectures, I'll see you in 2 weeks. Okay? Bye.